Hi everyone and welcome to this video series on cavity flow problem. This is a common programming exercise for those who are starting out in CFD, and by the end of this series you will have a clear understanding of how to solve this problem numerically and write a computer program to generate flow field and pressure field. In the first video we will go over the governing equations of fluid mechanics and apply a coordinate transformation to derive the stream function vorticity formulation, which is one of the simplest methods to solve this problem. In the upcoming videos, we will cover the discretization using finite difference method, setting up the boundary conditions, and in the final part of this series, we will bring everything together to program the solution in Python. So make sure you follow along for a complete understanding, and let's get started now. Before we dive deeper, for those who are completely new to this problem, let's first understand the physical setup of the situation. Imagine a perfectly cubical pit that is filled with the fluid. Now, if we start to drag the topmost layer of the fluid with some constant velocity, the fluid inside will start to swirl and vortices will be generated. The question we aim to answer here is what will be the flow field and pressure distribution look like in this situation. And it's important to note here that we are assuming no slip boundary condition at all the walls, meaning that there is no relative motion between the wall and fluid layer adjacent to the wall. Therefore, the velocity along the left, right and bottom wall is 0. And just for the sake of simplicity, we will take the top wall velocity or the velocity of the topmost layer of fluid as 1 meter per second. The equations that governs the fluid motion are the continuity equation and the momentum equation, which are shown here in the vector form. We cannot solve the momentum equation directly using the traditional analytical methods because of two main reasons. The first being that it is nonlinear due to the convective term present here, and the second is the pressure term. While we can manage the nonlinearity with numerical methods, but we need a strategy to deal with the pressure term. And the most effective strategy will be to eliminate it entirely. And now from the vector identity, since the pressure term is actually a gradient of a scalar function, so by taking the curl of the pressure term, it will reduce to 0. Because the curl of the gradient of a scalar function is 0. So now we will take curl on both the sides of the momentum equation. So here we have the momentum equation with curl operator on both the sides. And now let's open these brackets and expand the terms. For the first term with time derivative here, we can bring the curl operator inside the derivative as it is one of the vector identity. And for the convective term right here, the dot product between v and del, it acts as a scalar. So our curl operator will directly add on this second vector v right over here, and it is shown here. Similarly, on the right hand side, the curl operator will act on the pressure term, and for the diffusion term right over here, the curl can be safely brought inside these derivatives as we did for the time derivative term. And for the body force term, we can directly take the cross product between the del operator and the gravitational constant. Now this last term, the body force term, will vanish because of the fact that g is a constant vector and a curl of a constant vector gives a null vector. And also, as we discussed earlier, the curl when acted on the pressure term will reduce to 0. Again, it is one of the vector identities. And now from the definition of vorticity, which is nothing but the cross product of del operator and velocity field, we can substitute this relation in the above equation, and what we get is the vector form of the vorticity transport equation. We can write this in terms of coordinate or components, and it will look something like this. Now, since we are working in two dimensions, we can safely eliminate the terms involving the z derivative and z component of velocity. So here we have the vorticity transport equation written in two dimensions. Remember that our flow is two-dimensional in nature and we are also assuming it to be incompressible. So for two-dimensional incompressible flow, we can define the stream function psi in such a way that the y derivative of psi will give u and the negative of the x derivative of psi will give v. Remember that this minus sign right here is interchangeable. We can either put it with u or v, it doesn't matter. Also, the vector form of the vorticity when written for two-dimensional, particularly in x and y coordinates only, will consist only of its z component, and it is given by du by dy minus dv by dx. We can substitute u and v from here in this equation, and what we get is the Poisson equation that relates stream function and vorticity. We can also substitute u and v in the vorticity transport equation, and what we get is the final form of the vorticity transport equation. And these two equations together makes the stream function vorticity formulation that can be used to generate the flow field. So what we did here basically is that we changed our primary variables from u and v to new sets of variables that are omega and psi. This is a coordinate transform, and from now onwards we will work with psi and omega instead of u and v. So the Poisson equation and the vorticity transport equation that we derived till now will only help us to determine the flow field, but not the pressure field. So we need to derive a separate equation for pressure in terms of gradients of the velocity components, so that we can plot the pressure field. And here we have the vector form of the Navier-Stokes equation. And now let's extract the x component and the y component of momentum from this. We will differentiate the x momentum equation with respect to x on both the sides, and we will differentiate the y momentum equation with respect to y on both the sides. Here we have the x momentum and y momentum equation differentiated with x and y respectively. And now we will expand the brackets by taking derivatives of individual term in these equations, and when we will add both this equation, what we will get is the pressure Poisson equation to determine the pressure field. It's really simple exercise and you can do it on your own, but keep in mind the continuity equation, as you can substitute this while adding both this equation, and also the fact that the derivative of the gravitational term is 0. The pressure equation you will obtain will look something like this. But remember the fact that we are not anymore working with u and v, but we are working with psi and omega. So we can substitute u and v in terms of the derivatives of stream function, and the equation that we obtain at last will look something like this. And this is the pressure equation that will determine the pressure field in the domain. So to sum up, what we did till now was to determine the governing equation for the flow field and pressure field in terms of vorticity and stream function, that is omega and psi. That's all for this video, and in my next video I will discuss the finite difference method.